The monolithic phase locked loops, that means entire phase locked loops are in one IC, and that is Signetics SCNE 560 series. There are so many ICs: 560, 561, 62, 64, 65, and 67. SC bar NE 565 phase lock loop is here we are discussing, since it is the most commonly used devices. That is why it is discussed. And you can see the block diagram of and the pin configuration, as well as block diagram of um, SC bar NE 565. So here input, here you can see the phase comparator, and that is VCO input, phase comparator VCO input. Here you can have the VCO output. The fourth you can have VCO out. 5 is phase comparator VCO input. Then here you can have VCO R1 connected to plus V, C1 connected to minus V. In some cases we have to connect a resistor after phase detector amplifier. So here resistor 3.6 kilo ohm and C2, this forms a low pass filter. This will here at the 7 you will get the demodulated output and reference input. So according to the applications, you need to connect like this. Okay, you need to connect like this. You can see that input is connected to 2 and 3 is grounded. Plus V is 10 voltages, R1 10 kilo ohm, plus V it is directly connected to pin number 10. Through R1 it is connected to 8. Through C2 it is connected to 7. Between 8 and 7, C3, that is 0.001 microfarad. 7 you will get demodulated output, reference output. 4 VCO output, that is connected to 5, where as you can see the 5 is phase comparator VCO output. So this VCO output is again connected to 5, and 1 that is connected to minus V minus 10 voltage. Here C1 is 0.01 microfarad. So this is the basic connections. Now the important electrical characteristics of the 565 PLL are: operating frequency range 0.001 Hz to 500 kHz. Operating voltage range is plus or minus 6 to plus or minus 12 voltage. Input level required for tracking 10 millivolt RMS minimum to 3 voltage peak to peak maximum. Input level required for tracking 10 millivolt to 3 voltage. Input impedance 10 kilo ohm typically. Output sink current 1 milliamp typically. Output source current 10 milliamp typically. Source means it is giving out. Sink means it is taking. Drift in VCO center frequency of out with the temperature is 300 ppm per degree Celsius typically. Then drift in VCO center frequency with the supply voltage is 1.5% per V maximum. Then triangle wave Yeah. Triangle wave amplitude typically 2 volt peak to peak at a plus or minus 6 voltage. Yeah. Square wave amplitude typically 5.4 voltage peak at a plus or minus 6 voltage. Bandwidth adjustment range plus it should be greater than, it should be less than plus or minus 1 to greater than plus or minus 60 percentage. Now the center frequency of the PLL is defined by the free running frequency of the VCO, which is given by the free running frequency, or the center frequency of PLL is calculated by using F out is approximately equal to 1.2 divided by 4 into R1 into C1 Hertz. So here R1 and C1 are the external resistors and the capacitors connected to pin number 8 and 9 respectively. Pin number 8 and 9 respectively. Pin number 9 and 8 R1 C1. So that is decides this. Now the VCO free running frequency F out is adjusted externally with R1 and C1 to be at the center of the input frequency range. That means the VCO free running frequency F out is adjusted externally with, you can calculate R1 and C1 so that you can adjust it to the at the center of input frequency range. So according to the input frequency range, you can choose R1 and C1, and F out can be at the center. C1 can be any value, but R1 must be between 2 kilo ohm 20 kilo ohm. That already this is the case for VC also. A capacitor C2 connected between pin number 7 and the positive supply. Capacitor C2 connected between pin number 7 capacitor C2 connected between pin number 7 and the positive supply pin number 10, capacitor C2, form the first order low pass filter with an internal resistance of 3.6 kilo. There is an internal resistance here that already shown in the previous block diagram, that will form a first order low pass filter. Now the filter capacitor C2 should be large enough to eliminate variations in the demodulated output voltage at pin number 7. Demodulated output voltage pin number 7, it should be free from noise. Demodulated output voltage pin in order to stabilize the VCO frequency, eliminate the variations at pin number 7. This low pass filter, this capacitor C2 should be large enough to eliminate variations in the demodulated output voltage at pin number 7 in order to stabilize the VCO frequency. In order to stabilize the frequency, it should be free from the variation in frequency. So here, variation in frequency. Now the 565 PLL can log to and track the input signal over typically plus or minus 60% bandwidth with respect to F out as center frequency. So it can log and track. So here this figure is very important. At the center, that is the free running frequency F0. This is the capture range, this is the lock range. So this will be, yeah, so PLL can lock to and track an input signal over typically 60% bandwidth with respect to F out as the center frequency. The lock range FL and the capture range FC of the PLL are given by the following equation. FL is equal to lock range is this lock range is FL is plus or minus 8 F out by V hertz, where F out is free running frequency of VCO and V is plus V minus V volts, and FC capture range is equal to plus or minus FL divided by 2 pi 3.6 into 10 to the power of 3 C2 raised to half. So here, so that's about this PLL. Now we can see one problem. So here, referring to the circuit of figure, determine the free running frequency F out, lock range FL, and the capture range FC. So this diagram, you have to see C1 is here 0.01 microfarad, R1 is 12 kilo ohm, then C2 is 10 picofarad, but only I think that R1 and C1 is important. R1 and C1 only used in these formulas. You can see F out is 1.2 divided by 4 into R1 into C1. FL is 8 into F out by V. So you should understand V is plus 10 minus of minus 10, that is around 20 voltage. So FC is calculated plus or minus FL 2 pi 3.6. Here it is good. 10 to the power of 3 C2. C2 value also important, raised to half. And this diagram is very important. What is capture range? What is lock range? Okay, and you have to draw that also. Now first we will see F out. F out is nothing but 1.2 divided by 4 into R1 into C1. So 4 into R1 into C1. C1 is 0.01 microfarad, that is 1 into 10 to the power of minus 8, and R1 is 12 kilo ohm. So that you have to substitute there. So you will get a 12 into 10 to the power of 3. So you are getting 2.5 kilohertz. So that is marked as free running frequency of VCO output. That is as, you can mark it as 2.5 K V out. Okay, at the center. Now next you have to find FL. That is the lock range. Lock range is, what is FL? Everything definition already given. So plus or minus 8 into FL divided by V. V is plus 10 minus 10, plus V minus of minus V, that is 20. So it is, you will get plus or minus 1 kilohertz. So plus or minus 1 kilohertz with respect to your 2.5. 2.5 is here, plus or minus 1. So minus 1 means 1.5, plus 1 means 3.5. 2.5 plus 1, 3.5. 2.5 minus 1, 1.5. So this is the lock range. Then next one, you need to calculate the capture range. Capture range is calculated by plus or minus FL. FL is you got it as 1 kilohertz. Magnitude you have to consider, that is 10 to the power of 3 divided by 2 pi 3.6 into 10 to the power of 3 into C2. C2 is 10 10 microfarad. So 10 into 10 to the power of minus 6 raised to half, you will get plus or minus 66.49 hertz. This also related to your center frequency. So from this plus 66 plus you will get a plus or minus 66.49 hertz, not kilohertz. Okay, so 62.5 that is 2000, 2500 hertz. You have to add 66 hertz. You look into 2566 2.566 kilohertz. Here 2.5 minus 66, it will get to 2.433K. So this gives the capture range.